Hi everybody. So we are going to do a little bit with domain, asymptotes, and points of removable discontinuity. All right, so to begin with, let's talk about finding the domain. If you have a rational function, x squared minus 9 over x squared plus 6x plus 9, we don't want the denominator to be 0. We don't know how to divide by 0. So what we do is we take our denominator and we say, when does it not equal 0? In other words, we're trying to find when it does equal 0, so we're trying to avoid those values. Well, if you factor x squared plus 6x plus 9, you get x plus 3 times x plus 3. Okay? And they're both the same, so I just need to do this once. I'm going to subtract 3 on both sides, and I'm going to say, domain is don't use negative 3. Now, I'm going to do something, and I need you to catch that I'm tackling asymptotes and points of removable continuity kind of at the same time. And I'm going to give another example in a minute, and hopefully that clarifies. If after watching this video and you're stuck on it still, let me know, because I'm happy to dive farther into it. All right. So if I were to factor this, both top and bottom, I'd have x plus 3 times x minus 3 over x plus 3, x plus 3. And you'll notice that the factors x plus 3 cancel. It is normally the case that this is an indicator of a point of removable discontinuity. The issue is that we still have an x plus 3 left. And because the x plus 3 is still left, what's going to happen at x equals negative 3, you're going to have a vertical asymptote. I abbreviate it V period A period. Okay? So in a sense, the vertical asymptote is quote unquote a stronger object in mathematics than a point of removable discontinuity. Now, the vertical asymptote will happen at x equals negative 3. Your domain is stay away from negative 3. So if we wrote it in interval notation, which your book loves to do, it would be negative infinity to negative 3. And we would keep open parentheses because we don't want to include the negative 3. And then we unite that with negative 3 off to positive infinity. Okay? Now, we're going to deal with another function. So this one is x over x squared plus x minus 2. Now, factoring the bottom, you should get x minus 1 times x plus 2. And these x minus 1's cancel. All right, let's address that. At x minus 1, it would equal 0, or you'd have x equals 1. You'd add 1 to both sides. And because this cancels, and there's no other factor x minus 1 in there, this is a point of removable discontinuity, or removable point of discontinuity. Again, depends on the author. I'm not wed to either, so you can just address it that way. And what's going to happen there, if you graph y is equal to x minus 1, make sure you put it in parentheses, divided by x squared plus x minus 2, you do it on your calculator, and you hit the second key and the trace key, and then hit value, and it'll say x equals 1. You won't get any y value out. And what's happening at x equals 1 is you have a hollow dot rather than a vertical asymptote. So you would graph a hollow dot at x equals negative 2. Now, what the y value, at the 1, and what the y value would be if it actually, or where you put the hollow dot, that's the way I need to say it. So where you put the hollow dot is you take the 1 and you plug it into the reduced equation, and you'll end up at 1/3. So at 1 comma 1/3, that's where your hollow dot would sit. Also, because the x plus 2 is still remaining in your reduced equation, or your reduced version of the original equation, you'll have a vertical asymptote at x equals -2. Your domain in this instance will be the following. And it comes from setting each of these factors equal to 0. So we're going to say, don't have -2 and don't have +1. We're going to stay away from those values. So we put the not equals. In interval notation, it's going to look like this. -infinity to -2, united with -2 to 1, united with 1 off to infinity. And again, open parentheses for all of them, because we can't include the -2 and we can't include the 1. Okay, hopefully that helps a little bit.